let's talk about potential energy. And we're going to talk about these types of potential energy. 3 examples: elastic, chemical, and gravitational. And by potential, we mean it's not really using it, it's stored energy. Okay? So this object can be storing this energy, and then when we need it, we could get that energy from it. So think of like a battery. A battery stores energy. When I turn on the flashlight, I get energy from it. So the battery has potential energy because in its stored state, it has the potential to do work. It's not doing any work, but it has the potential. I think I know some students like that. All right, so let's talk about elastic potential energy. Elastic potential energy, when we're talking about something that can be stretched or compressed. And, it doesn't necessarily have to be a spring. I mean, even a ball, for instance, has, elastic potential energy. And, they talk about the bow. If I pull the bow back, I'm storing that energy. Or a rubber band has, potential energy. If I stretch it and don't let go of it, it has potential energy at that case, in that state. Chemical energy would be energy in things like fuels. We talk about gasoline, talked about batteries, those kind of things. Sometimes it's just in the arrangement of the electrical charges, or it's when a chemical change takes place. I put 2 things together, I get this reaction, and in that process I get heat or something else. And those are examples of chemical energy. And when they're just being stored, that's potential. And then the 3rd example they talk about is gravitational potential energy. And this is the most common thing that we talk about. If we're talking about, an object that's lifted up above the earth, it has potential to fall and do some work when it hits the ground and so on. So that is gravitational potential energy. And we use that when we, do things as simple as we dam up a lake or a river to get, to create a hydroelectric plant, like Hoover Dam. Or they talk about the pile driver here. All of those are examples of potential energy. We're talking about gravitational potential energy. My formula is mgh. Potential energy equals the mass times gravity times the height. Now, on the Earth, really mg, that's our weight. So on the Earth, it's simply your weight times the height. Well, think about this. Weight is a force. Height is a distance. And we said that work was force times distance. And so that's what we're talking about. And work is energy. It takes energy to do work. Okay, note that the height is the distance above. In other words, what we're saying is this is all relative. Okay? So typically we might be talking about the ground. That's the potential energy it has in case of the ground. But, our ground here is not the same height. This is the ground in Denver and so on. So, it's relative to whatever you pick for potential energy in terms of gravitational potential energy. Also, be aware that it doesn't really matter how I get it there. In other words, I could lift this boulder straight up. It's got 200 joules of energy. It's a 100 Newton boulder. I've lifted it 2 meters. Gives me 200 joules of energy. I could also roll it up a ramp. Now notice the ramp is longer. Here this was 2 meters. This is 4 meters. But here's what happens. Rolling it up the ramp, I don't have to apply as much force. I'm only going to apply 50 newtons of force. But I'm going to do that over 4 meters of distance. I'm still getting 200 joules of work out of that particular example there. And in the 3rd example, it says, hey, if I do this up the stairs, so I do, this one first. Now that's going to be, maybe that's half a meter, and so I've done 50 joules of work there, and 50 here, and 50 here, and 50 here. But eventually, I've done 200. So it doesn't really matter whether I just lift it straight up, go up a ramp, go upstairs. Notice that we have these in our life all the time, and we have stairs, we have ramps, because what we're trying to do is lower, either here we're lowering the amount of force that I have to apply, or here we're breaking it up. Obviously, 2 meters is pretty high. I need something to get up there. So a lot of times we do it for us to make it easier. And we'll get into that when we talk about machines. All right, another example, hydroelectric power. We use gravitational potential energy. So the water's in an upper reservoir, goes down through a generator to a lower reservoir. I mean, go look at pictures of Hoover Dam. This thing is just huge, and you got this big, huge dam here, and the water comes out down here, and you have this water level way up here, and so the water goes through their generator and comes out at the bottom, and we get all that energy, from this height, and this thing is hundreds of feet tall. I don't remember exactly how tall it is, but it's huge, and so it's going to create all of this energy as the water falls through there. You can turn a turbine and so on. Another thing that power stations do is sometimes they buy the electricity when it's cheap at night, nobody's using it, pump it up, the water up there so that they can store it, and then get it back out when they need it. And that way you don't have these huge demands on electricity when when everybody wants to use their air conditioners or so on. All right, so think, you left a 100 Newton boulder 1 meter. How much work did you do? And what power is expended if you lift the boulder in a time of 2 seconds? And what is the gravitational potential energy of the boulder in the lifted position? All right, so stop the tape and work on those, see if you can figure them out. All right, so here we go. Work is force times distance, so my work would be 100 joules. Power, we did 100 joules of work in 2 seconds, okay? 2 seconds. So therefore, 100 divided by 2 is 50 watts. So about like a light bulb. And relative to its starting position, the boulder's potential energy is 100 joules, okay? So it has 100 joules of potential energy because I did 100 joules of work on it. The kinetic, 9.5, kinetic energy. And when we're talking about kinetic energy, we're talking about energy of motion. So something has to be moving in order to have kinetic energy. And here's a new formula, one for you to remember. Kinetic energy is 1/2 mv squared. 1/2 times the mass times the velocity squared. Notice if you are not moving, you have no velocity, you would have no kinetic energy. At that point, you might have some potential energy or something else, but you do not have kinetic energy. And if you have kinetic energy, velocity is moving, notice what happens. Notice the fact that it's a squared term. So if you double your velocity, you're going to get 4 times the potential or kinetic energy. We'll talk about that here in just a minute. So you throw a ball, you apply a force over a distance. You've done so much work in that example. You've done a certain amount of work. And that work is now changed into kinetic energy because the ball is now moving. Okay. Now, here's what we were talking about. If I double the velocity, I get 4 times the energy. So as I keep going up and up and up in terms of velocity, I get more and more energy. So in other words, think about this. If I want to take a car going at 10 meters per second and increase it to 20 meters per second, I haven't just doubled how much kinetic energy it has. I've actually got 4 times the amount of kinetic energy. So I would have to put in a lot more work. I don't just double the amount of work I had to put into it, or the amount of energy I put into it. I double more, which is why you don't get as good a gas mileage the faster you go, because it takes more energy to keep it going that fast.